Imagine the most powerful cosmic objects in the universe, born from the explosive deaths of massive stars. These are neutron stars, and they're so dense that a single teaspoon of their material would weigh 1 billion tons on Earth. But here's where it gets even more fascinating. Some of these neutron stars spin hundreds of times per second, and they beam out intense radiation like cosmic lighthouses. We call these pulsars, and their story is one of the most incredible in astrophysics. Stick around, because we're about to dive into the mind-bending world of neutron stars and pulsars, and trust me, you won't want to miss this. The birth of neutron stars. Neutron stars are among the most fascinating objects in the universe. They are born from the remnants of massive stars that have gone supernova. When a star several times more massive than our Sun exhausts its nuclear fuel, it can no longer counteract the immense gravitational forces pulling it inward. The core collapses, and the outer layers are blasted into space in a spectacular explosion. What remains is an incredibly dense core, primarily composed of neutrons, packed so tightly that a teaspoon of neutron star material would weigh billions of tons on Earth. The formation of a neutron star is a dramatic event. As the core collapses, protons and electrons are crushed together to form neutrons, releasing a vast amount of energy in the process. This collapse is halted only when the neutrons themselves resist further compression, creating an incredibly dense object. Neutron stars are typically around 10 to 20 kilometers in diameter, yet they can have a mass up to about twice that of the Sun. Their density is so extreme that a sugar cube-sized amount of neutron star material would weigh about 1 billion tons on Earth. Pulsars are a special type of neutron star that emit beams of electromagnetic radiation. These beams are generated by the neutron star's magnetic field, which is incredibly strong, billions of times more powerful than Earth's. As the neutron star rotates, these beams sweep through space like the light from a lighthouse. If one of these beams happens to sweep across Earth, we detect it as a regular pulse of radiation. This is why these objects are called pulsars, short for pulsating stars. The pulses are extremely regular, making pulsars some of the most precise clocks in the universe. The lighthouse analogy is particularly pertinent. Just as a lighthouse's rotating light appears to flash as it sweeps across the landscape, a pulsar's rotating beams of radiation appear to pulse as they sweep across our line of sight. The frequency of these pulses is directly related to the neutron star's rotation rate. Some pulsars spin incredibly fast, with rotation periods measured in milliseconds. These are known as millisecond pulsars. Others spin more slowly, with periods ranging from a few seconds to several minutes. The study of pulsars has provided valuable insights into the physics of neutron stars, the nature of matter at extreme densities, and even the very fabric of spacetime itself. Supernovae, cosmic cataclysms. In the vast expanse of the universe, stars lead dramatic lives, and their deaths can be as spectacular as their births. Supernovae, the explosive deaths of massive stars, are among the most cataclysmic events in the cosmos. These stellar explosions release an enormous amount of energy, outshining entire galaxies for brief periods. The remnants of these explosions can give birth to some of the most enigmatic objects in the universe, neutron stars and pulsars. When a massive star exhausts its nuclear fuel, it can no longer counteract the immense gravitational forces pulling its core inward. The core collapses under its own weight, triggering a supernova explosion. This violent event blasts away the star's outer layers, leaving behind an incredibly dense remnant. If the remaining core is between about 1.4 and 3 times the mass of the Sun, it becomes a neutron star. Neutron stars are incredibly dense, with a teaspoon of neutron star material weighing billions of tons. They are so dense that protons and electrons in the star's core combine to form neutrons, hence the name. The formation of a neutron star is a rapid process, taking just a few seconds. During this time, the core collapses to a radius of about 10-20 kilometers, while its density skyrockets. The intense gravitational collapse also causes the neutron star to spin rapidly, often hundreds of times per second. This rapid rotation is a key feature that gives rise to pulsars. Pulsars are a type of neutron star that emit beams of electromagnetic radiation. These beams are generated by the neutron star's magnetic field, which is incredibly strong, trillions of times stronger than Earth's. As the neutron star spins, these beams sweep through space like a lighthouse's beam sweeping across the sea. When one of these beams points towards Earth, astronomers detect a pulse of radiation. This is why these objects are called pulsars. They appear to pulse on and off as their beams sweep past us. The regularity of these pulses is astonishing, making pulsars some of the most precise clocks in the universe. Some pulsars spin at incredibly stable rates, losing only a few milliseconds over millions of years. This precision makes them valuable tools for astronomers studying gravitational waves, general relativity, and other fundamental aspects of the universe. The lighthouse analogy is particularly pertinent. Just as a lighthouse's beam rotates and periodically sweeps over an observer, a pulsar's beam of radiation rotates and periodically points towards Earth. The difference is that a lighthouse's beam is visible to the naked eye, while a pulsar's beam is typically detected in radio wavelengths, though some pulsars also emit visible light, X rays, and gamma rays. The study of neutron stars and pulsars has revealed much about the extreme conditions in the universe. These objects push the boundaries of known physics, providing insights into the behavior of matter and energy under extreme densities and magnetic fields. For instance, the study of pulsars has led to the discovery of exoplanets, or planets outside our solar system. In 1992, astronomers found the first confirmed exoplanets orbiting a pulsar known as PSR B1257+12. This discovery opened a new window into the diversity of planetary systems and challenged existing theories about planet formation. Moreover, pulsars are used as natural laboratories for testing Einstein's theory of general relativity. Their extreme gravitational fields allow astronomers to probe the fabric of space-time itself. For example, the double pulsar system PSR J0737-3039, where two pulsars orbit each other, provides a unique opportunity to study the effects of gravitational waves and the nature of gravity. The study of neutron stars and pulsars continues to be a vibrant field of research, offering tantalizing glimpses into the cosmos's most extreme and mysterious phenomena. Gravitational collapse. In the grand theater of the cosmos, neutron stars and pulsars are among the most enigmatic performers. They are born from the dramatic death throes of massive stars, a process known as gravitational collapse. When a star several times more massive than our Sun exhausts its nuclear fuel, it can no longer withstand its own gravitational pull. The outer layers collapse inward at speeds up to 23% of the speed of light, and the core compresses to extreme densities. This collapse is so violent that it triggers a supernova explosion, leaving behind a remnant core. If this core's mass is between about 1.4 and 3 times that of the Sun, it becomes a neutron star, an object so dense that a teaspoon of its material would weigh around 1 billion tons on Earth. Neutron stars are incredibly compact, with diameters of about 12-24 kilometers, yet they possess immense gravitational fields. Their formation involves a complex interplay of forces. As the core collapses, protons and electrons combine to form neutrons, hence the name neutron star. The collapse is halted when neutron degeneracy pressure, the quantum mechanical resistance of neutrons to being packed too closely together, balances the gravitational force. This process is not always smooth. Sometimes, it results in a rapid spin, with some neutron stars rotating hundreds of times per second. Pulsars are a subset of neutron stars that emit beams of electromagnetic radiation. These beams are observed as pulses of radiation, much like the rotating beam of a lighthouse. The mechanism behind pulsars involves their intense magnetic fields and rapid rotation. As a neutron star spins, its magnetic field exerts forces that cause charged particles to accelerate along the magnetic field lines, producing radiation. This radiation is emitted in narrow cones aligned with the magnetic poles. If these cones sweep past Earth, we detect them as regular pulses. The precision of these pulses is astonishing. Some pulsars are as accurate as atomic clocks. The study of neutron stars and pulsars has provided profound insights into the nature of matter under extreme conditions. Their gravitational fields are so strong that they warp space-time, offering a natural laboratory for testing Einstein's theory of general relativity. Moreover, Pulsars serve as cosmic clocks, helping scientists study phenomena like gravitational waves and the interstellar medium. The lighthouse analogy is particularly apt, as pulsars not only guide astronomers through the cosmos, but also illuminate the fundamental laws of physics. The density enigma. Neutron stars are among the densest objects in the universe, cramming the mass of the Sun into a sphere no larger than a city. They form from the remnants of massive stars that have gone supernova, leaving behind a core so dense that protons and electrons are crushed together, forming neutrons. This process is so extreme that a single teaspoon of neutron star material would weigh billions of tons on Earth. The density enigma lies in the fact that, despite our understanding of their formation, the exact nature of matter inside neutron stars remains a mystery. Scientists theorize that the core might be composed of exotic particles or states of matter, but direct observation is currently beyond our capabilities. Pulsars, a subset of neutron stars, act like cosmic lighthouses, emitting beams of radiation that sweep through space as the star rotates. These beams are generated by the neutron star's intense magnetic field, which accelerates charged particles and produces powerful electromagnetic radiation. The regularity of these pulses is astonishing, with some pulsars ticking like cosmic clocks, their periods measured with extreme precision. The lighthouse analogy is apt. Just as a lighthouse's rotating beam sweeps across the landscape, a pulsar's beam sweeps across the sky, appearing to pulse when it points towards Earth. This mechanism allows astronomers to study the properties of neutron stars and test theories of fundamental physics. The density enigma is further complicated by the behavior of matter under such extreme conditions. Neutron stars can exhibit phenomena like glitches, where their rotation suddenly speeds up, or starquakes, which are analogous to earthquakes, but on a stellar scale. These events provide clues about the internal structure of neutron stars, but interpreting them requires sophisticated models and simulations. Additionally, the discovery of pulsars in binary systems has revealed phenomena like accretion disks and relativistic jets, offering insights into the dynamics of these extreme environments. Despite these advancements, the exact nature of the ultradense core remains elusive, driving ongoing research and theoretical exploration. Neutron star composition. Neutron stars are among the most exotic and fascinating objects in the universe. Born from the fiery deaths of massive stars, these celestial bodies are incredibly dense, with a teaspoon of neutron star material weighing billions of tons on Earth. Their composition is predominantly neutrons, hence the name, packed so tightly that they defy ordinary understanding of matter. The core of a neutron star is a soup of neutrons, protons, and other subatomic particles, while the outer crust is composed of heavy atomic nuclei. This extreme density means that a neutron star with a radius of about 10 kilometers can have a mass up to twice that of the Sun. The formation of a neutron star is a dramatic event. It begins with a supernova explosion, the violent end of a massive star's life. When the star's core collapses under its own gravity, it compresses to such an extent that protons and electrons combine to form neutrons, releasing a burst of neutrinos. This collapse is so rapid that it creates a shock wave, causing the outer layers of the star to explode in a supernova. The remaining core, now a neutron star, is left spinning rapidly due to the conservation of angular momentum. This rapid spin is a key characteristic that leads to the phenomenon of pulsars. Pulsars are a type of neutron star that emit beams of electromagnetic radiation. These beams are generated by the neutron star's magnetic field, which is incredibly strong, billions of times stronger than Earth's. As the neutron star spins, these beams sweep through space like the light from a lighthouse. If one of these beams points towards Earth, we detect it as a regular pulse of radiation, hence the name pulsar. The pulses are incredibly precise, making pulsars some of the most accurate natural clocks known. Some pulsars spin hundreds of times per second, while others spin more slowly. The fastest known pulsar, PSRJ 1748-2446 AD, spins at over 700 times per second. The lighthouse analogy is particularly apt for understanding pulsars. Just as a lighthouse's rotating light sweeps across the landscape, a pulsar's beams sweep across the cosmos. The beams are typically emitted from the magnetic poles of the neutron star, which are not aligned with its rotational axis. This misalignment causes the beams to sweep in a conical pattern, much like the light from a lighthouse. The periodicity of the pulses is directly related to the neutron star's spin rate. For example, if a pulsar spins 10 times per second, its beams will sweep past Earth 10 times per second, resulting in 10 pulses per second. This regularity makes pulsars invaluable tools for studying a wide range of astrophysical phenomena, from testing theories of gravity to searching for gravitational waves. Crust and core. Neutron stars are among the most fascinating objects in the universe. They form from the remnants of massive stars that have gone supernova. When a star several times more massive than our Sun exhausts its nuclear fuel, it collapses under its own gravity. The outer layers explode in a supernova, while the core collapses into an incredibly dense neutron star. A single sugar cube-sized amount of neutron star material can weigh as much as a mountain. This extreme density means that the star's protons and electrons combine to form neutrons, hence the name. The structure of a neutron star is divided into two main regions, the crust and the core. The crust is incredibly thin, often just a kilometer or so thick, but it's incredibly strong. It's composed of a lattice of atomic nuclei and electrons. Deeper down, the density increases, and the matter becomes a superfluid of neutrons. The core, on the other hand, is a seething, ultra-dense soup of neutrons, protons, and other exotic particles. It's here that the star's magnetic field is generated, and it's this field that plays a crucial role in the behavior of pulsars. Pulsars are a type of neutron star that emit beams of electromagnetic radiation. These beams are often focused along the star's magnetic poles. As the star rotates, these beams sweep through space like a lighthouse. If one of these beams points towards Earth, we detect it as a pulse of radiation. This is why pulsars appear to pulse, even though they're emitting radiation continuously. The pulses are incredibly regular, making pulsars useful for studying gravity, space-time, and even detecting gravitational waves. The lighthouse analogy is particularly pertinent. Just as a lighthouse's beam rotates and sweeps across the landscape, so too do the beams of radiation from a pulsar. The difference is that a lighthouse's beam is visible for a fraction of a second, while a pulsar's beam can be detected for minutes or even hours. Moreover, the beam from a pulsar is not visible light, but often radio waves, tinth rays, or gamma rays. The rotation of the pulsar is what creates the pulsing effect. Some pulsars rotate incredibly fast, with some completing hundreds of rotations per second. These are known as millisecond pulsars. The fastest known pulsar, PSRJ 1748-2446 AD, rotates at over 700 times per second. Magnetic fields, invisible titans. Neutron stars are among the most fascinating objects in the universe. They form from the remnants of massive stars that have gone supernova. When a star many times more massive than our Sun exhausts its nuclear fuel, it collapses under its own gravity. The outer layers explode in a supernova, while the core compresses to an incredibly dense state, creating a neutron star. These stars are so dense that a teaspoon of neutron star material would weigh billions of tons on Earth. Their formation is a violent and energetic process, releasing vast amounts of energy and matter into space. Pulsars are a special type of neutron star that emit beams of electromagnetic radiation. These beams are generated by the neutron star's intense magnetic field, which is billions of times stronger than Earth's. As the neutron star rotates, these beams sweep through space like a lighthouse beam. If one of these beams points towards Earth, we detect it as a pulsar. The regularity of these pulses is astonishing, making pulsars some of the most precise clocks in the universe. Some pulsars spin hundreds of times per second, while others rotate more slowly. The mechanism behind pulsars involves the neutron star's magnetic field and its rapid rotation, which accelerates charged particles and produces the observed radiation. The magnetic fields of neutron stars are truly titanic. These fields are so strong that they can distort the very fabric of space-time. They play a crucial role in the behavior of neutron stars and pulsars. The magnetic field lines of a neutron star can trap charged particles, creating a complex and dynamic environment. This environment can lead to the emission of various types of radiation, including 10th rays and gamma rays. The interaction between the magnetic field and the neutron star's rotation can also create powerful winds of particles that stream out into space. These winds can influence the surrounding interstellar medium and even shape the evolution of the neutron star's surroundings. The lighthouse analogy is particularly apt for describing pulsars. Just as a lighthouse's rotating beam sweeps across the landscape, a pulsar's beams of radiation sweep across the cosmos. The regularity of these pulses is a result of the neutron star's precise rotation. Some pulsars are so regular that they rival atomic clocks in their accuracy. This precision makes pulsars valuable tools for astronomers. They can be used to study the interstellar medium, test theories of gravity, and even search for gravitational waves. The study of pulsars has led to numerous discoveries and has deepened our understanding of the universe. Pulsars, the lighthouse effect. Neutron stars are among the most exotic and fascinating objects in the universe. They form from the remnants of massive stars that have gone supernova. When a star much more massive than our Sun exhausts its nuclear fuel, it can no longer counteract the immense force of gravity pulling its core inward. The core collapses, and the outer layers are blasted into space in a spectacular explosion. What remains is an incredibly dense core, a neutron star. A teaspoon of neutron star material would weigh billions of tons on Earth. These stars are so dense that their gravity bends the surrounding space-time, and they often spin rapidly, sometimes hundreds of times per second. Pulsars are a special type of neutron star that emit beams of electromagnetic radiation. These beams are not constant, but rather sweep through space like the light from a lighthouse. The mechanism behind this lighthouse effect is the rapid rotation of the neutron star. As the star spins, its magnetic field generates intense electric fields that accelerate charged particles, producing powerful beams of radiation. These beams can include radio waves, 10th rays, and even gamma rays. The beams are not aligned with the star's rotational axis, but rather with its magnetic axis, which is often tilted. This misalignment causes the beams to sweep through space like a cosmic searchlight. The lighthouse analogy is particularly pertinent. Just as a lighthouse's rotating light appears to flash as it sweeps across the landscape, a pulsar's beams appear to pulse as they cross our line of sight. The interval between pulses is incredibly regular, making pulsars some of the most precise clocks in the universe. Astronomers have used this regularity to study a wide range of phenomena, from testing theories of gravity to detecting gravitational waves. The pulses can be as brief as milliseconds, and their regularity can be as precise as atomic clocks. This precision has made pulsars invaluable tools for astronomers. The study of pulsars has also led to some surprising discoveries. For instance, the first planet ever discovered outside our solar system was found orbiting a pulsar. The slight variations in the timing of the pulses revealed the presence of the planet, showcasing the incredible sensitivity of pulsar observations. Additionally, pulsars can exist in binary systems, where they interact with a companion star. These interactions can lead to phenomena like 10th ray binaries, where the pulsar's intense gravity pulls material from the companion star, creating a brilliant display of high-energy radiation. The study of these systems has provided insights into the physics of extreme environments and the nature of matter under extreme conditions. Rotational dynamics. Neutron stars are among the densest objects in the universe, formed from the remnants of massive stars that have gone supernova. These stellar corpses pack the mass of the Sun into a sphere roughly the size of a city, creating a gravitational pull billions of times stronger than Earth's. The formation process is violent and rapid, with the star's outer layers exploding outward while the core collapses under its own gravity. This collapse is so intense that protons and electrons are crushed together, forming neutrons and neutrinos. The result is a neutron star, a name that reflects its predominantly neutron composition. Pulsars are a subset of neutron stars that emit beams of electromagnetic radiation. These beams are generated by the star's magnetic field, which is incredibly strong, millions to trillions of times more powerful than Earth's. As the neutron star rotates, these beams sweep through space like a lighthouse's light. If one of these beams happens to point toward Earth, we detect it as a pulsar. The regularity of these pulses is astonishing, with some pulsars ticking like cosmic clocks, their periods measured in milliseconds. This precision makes them invaluable tools for studying gravitational waves, testing general relativity, and even navigating spacecraft. The rotational dynamics of pulsars are governed by their initial spin rate and subsequent slowdown due to electromagnetic radiation and particle winds. When a neutron star forms, it can spin incredibly fast, with some pulsars rotating hundreds of times per second. Over time, the pulsar's rotation slows down due to the emission of energy in the form of radiation and particles. This process, known as a spin-down, is a key area of study in astrophysics. The rate of slowdown can provide insights into the pulsar's magnetic field strength, age, and even the properties of the interstellar medium. The lighthouse analogy is particularly apt for understanding pulsars. Just as a lighthouse's rotating light sweeps across the landscape, a pulsar's beams sweep across the cosmos. The difference is that lighthouses rotate relatively slowly, while pulsars can spin at mind-boggling speeds. The beams themselves are not continuous, but rather pulses of radiation, which can include radio waves, X rays, and even gamma rays. The exact mechanism behind the beam's generation is still an active area of research, but it is believed to involve complex interactions between the star's magnetic field and its intense gravitational field. Understanding these dynamics is crucial for unraveling the mysteries of these cosmic lighthouses. Lighthouse mechanics. Neutron stars are among the most fascinating objects in the universe. They form from the remnants of massive stars that have gone supernova. When a star many times more massive than our Sun exhausts its nuclear fuel, it can no longer counteract the immense gravitational forces pulling its core inward. The core collapses, and the outer layers are blasted into space in a spectacular explosion. What remains is an incredibly dense core, a neutron star. A teaspoon of neutron star material would weigh billions of tons on Earth. These stars are so dense that protons and electrons in their cores combine to form neutrons, hence the name. Pulsars are a special type of neutron star that emit beams of electromagnetic radiation. These beams are not constant, but rather sweep through space like the light from a lighthouse. The mechanism behind this behavior is the neutron star's rapid rotation and strong magnetic field. Neutron stars can rotate hundreds of times per second. As they spin, their magnetic fields create intense electric fields that accelerate charged particles, producing powerful beams of radiation. These beams are emitted from the magnetic poles of the neutron star. However, these poles are not aligned with the star's rotational axis, causing the beams to sweep through space like a lighthouse beam sweeping across the horizon. The lighthouse analogy is particularly pertinent. Just as a lighthouse's rotating light appears to flash as it sweeps across the observer, a pulsar's beam appears to pulse as it crosses our line of sight. The interval between pulses is incredibly regular, making pulsars some of the most precise clocks in the universe. Some pulsars spin at rates of up to 700 times per second, while others spin more slowly. The fastest spinning pulsars are known as millisecond pulsars. They are often found in binary star systems, where they have been spun up to such high speeds by accreting material from their companion stars. The study of pulsars has provided valuable insights into the nature of matter under extreme conditions. Pulsars also serve as natural laboratories for testing theories of gravity and general relativity. Their precise timing allows scientists to detect subtle effects, such as the presence of planets orbiting pulsars. In fact, the first exoplanets ever discovered were found orbiting a pulsar. Moreover, pulsars are used to study the interstellar medium, as the dispersion of their signals provides information about the electron density between the stars. This makes them invaluable tools for astronomers. Pulsar radiation. Neutron stars, the ultra-dense remnants of massive stars that have gone supernova, are among the most extreme objects in the universe. These celestial bodies are so dense that a single teaspoon of neutron star material would weigh billions of tons on Earth. They form when the core of a massive star collapses under its own gravity, compressing the star's material into a sphere with a radius of about 10-20 kilometers. The gravitational pull on the surface of a neutron star is so strong that it can distort the space-time continuum around it. Some neutron stars exhibit a fascinating phenomenon. They emit beams of electromagnetic radiation that sweep through space like a lighthouse's beam. These objects are known as pulsars. Pulsars are highly magnetized, rotating neutron stars that emit radiation in narrow beams. The radiation is emitted from the magnetic poles of the pulsar, which are not aligned with its rotational axis. As the pulsar spins, these beams of radiation sweep across the cosmos, and if one of these beams points towards Earth, we detect it as a pulse of radiation. This regular pulsing is incredibly precise, making pulsars some of the most accurate natural clocks known. The radiation emitted by pulsars spans a wide range of the electromagnetic spectrum, from radio waves to gamma rays. The exact mechanism behind this radiation is complex and involves a combination of factors. The intense magnetic field of the pulsar accelerates charged particles to near the speed of light. These particles then interact with the magnetic field, producing the observed radiation. The beams are highly collimated, meaning they are focused into narrow jets. This collimation is thought to be due to the intense magnetic fields and the rapid rotation of the pulsar. The lighthouse analogy is particularly apt here, as the beams are not continuous but rather pulsate as the pulsar spins, creating a regular, rhythmic signal that can be detected by astronomers. Pulsars can spin at incredibly high speeds, with some rotating hundreds of times per second. The fastest known pulsar, PSRJ 1748-2446 AD, spins at a mind-boggling 716 times per second. This rapid rotation is a result of the conservation of angular momentum during the star's collapse. As the star's core collapses, it spins faster, much like an ice skater pulling in their arms to spin faster. The radiation beams emitted by pulsars are not uniform, but often exhibit complex patterns and variations. These variations can provide valuable insights into the physical processes occurring within the pulsar and its magnetosphere. By studying these patterns, astronomers can probe the extreme conditions near neutron stars and test theories of matter and energy in extreme environments. The role of magnetism. Neutron stars are among the most magnetic objects in the universe. Born from the supernova explosions of massive stars, these incredibly dense remnants pack the mass of the Sun into a sphere just a few kilometers across. Their magnetic fields can be trillions of times stronger than Earth's. This immense magnetism plays a crucial role in the behavior of neutron stars, particularly in the formation of pulsars. Pulsars are a type of neutron star that emits beams of electromagnetic radiation. These beams sweep through space like the light from a lighthouse, and when one of these beams points towards Earth, it creates a regular pulse of radiation that we can detect. The mechanism behind pulsars is intrinsically linked to the neutron star's rapid rotation and intense magnetic field. When a massive star collapses to form a neutron star, it can start spinning extremely fast, sometimes hundreds of times per second. This rapid rotation, combined with the star's powerful magnetic field, creates an incredibly dynamic environment. Charged particles, primarily electrons and positrons, are accelerated along the magnetic field lines near the neutron star's magnetic poles. These particles emit intense beams of radiation, including radio waves, tinth rays, and gamma rays. As the neutron star rotates, these beams sweep through space, creating the pulse signals that give pulsars their name. The lighthouse analogy is particularly apt for describing pulsars. Just as a lighthouse's rotating light appears to flash as it sweeps across the landscape, a pulsar's rotating beams of radiation appear to pulse as they cross our line of sight. The regularity of these pulses is astonishing, with some pulsars ticking like cosmic clocks, their periods measurable to within microseconds. This precision makes pulsars invaluable tools for astronomers. They are used to study the interstellar medium, test theories of gravity, and even detect gravitational waves. The magnetism of neutron stars is the driving force behind this cosmic phenomenon, shaping the behavior of these enigmatic objects and providing a window into the extreme physics of the universe. Moreover, the magnetism of neutron stars can have profound effects on their surroundings. The intense magnetic fields can create powerful winds of charged particles that interact with the interstellar medium, creating complex structures and emitting a variety of radiation. In some cases, these magnetic fields can be so strong that they distort the very fabric of space-time, creating phenomena that challenge our understanding of physics. The study of neutron stars and pulsars continues to push the boundaries of our knowledge, revealing the intricate dance of matter, energy, and magnetism in the cosmos. Pulsar timing. Neutron stars are among the most fascinating objects in the universe. They form from the remnants of massive stars that have gone supernova. When a star several times more massive than our Sun exhausts its nuclear fuel, it collapses under its own gravity. This collapse triggers a supernova explosion, leaving behind a dense core. If the core's mass is between about 1.4 and 3 times that of the Sun, it becomes a neutron star. These stars are incredibly dense, with a teaspoon of neutron star material weighing billions of tons on Earth. Their gravity is so strong that it crushes protons and electrons together, forming neutrons. This is why they're called neutron stars. Pulsars are a special type of neutron star that emit beams of electromagnetic radiation. These beams are often observed as pulses of radiation, hence the name pulsar. The pulses occur because pulsars spin rapidly, and their magnetic fields funnel jets of particles out along their magnetic poles. These jets produce the observed beams of radiation. If the beams sweep past Earth, we detect them as regular pulses. This is akin to a lighthouse, where the rotating light appears to flicker as it sweeps across an observer's line of sight. Pulsars can spin incredibly fast, with some completing hundreds of rotations per second. The fastest known pulsar, PSRJ 1748-2446 AD, spins at over 700 times per second. Pulsar timing is a precise method used to study these cosmic lighthouses. Pulsars are known for their extreme regularity. Some pulsars are as precise as atomic clocks. This precision makes them valuable tools for astronomers. By carefully measuring the arrival times of pulses, scientists can study various phenomena. For instance, pulsar timing has been used to detect gravitational waves, study the interstellar medium, and even search for planets around pulsars. In one notable example, the first planets ever discovered outside our solar system were found orbiting a pulsar, PSR B1257+12. The slight variations in the pulsar's timing revealed the presence of these planets. The study of pulsar timing has also led to the development of pulsar timing arrays. These are groups of pulsars spread across the sky, monitored for subtle changes in their pulse arrival times. These arrays act like galactic-scale gravitational wave detectors. They can pick up the faint ripples in space-time caused by supermassive black hole mergers. This is an exciting area of research, as it opens a new window into the universe. Pulsar timing arrays could one day help us understand the evolution of galaxies and the nature of gravity itself. The precision and regularity of pulsars make them invaluable tools for exploring the cosmos. Their study continues to push the boundaries of our understanding of the universe. Pulsar glitches. Neutron stars are among the most fascinating objects in the universe. They form from the remnants of massive stars that have gone supernova. When a star many times the mass of our Sun exhausts its nuclear fuel, it collapses under its own gravity, triggering a catastrophic explosion. The core of the star, now incredibly dense, collapses further, crushing electrons and protons together to form neutrons. This process leaves behind a city-sized object with the mass of 1 to 2 suns, known as a neutron star. The density is so extreme that a teaspoon of neutron star material would weigh billions of tons on Earth. Some neutron stars exhibit a remarkable behavior, spinning rapidly and emitting beams of electromagnetic radiation. These are known as pulsars. Think of them as cosmic lighthouses. As the neutron star spins, the beams of radiation sweep through space like the light from a lighthouse. When one of these beams crosses our line of sight, we detect it as a regular pulse of radiation. The precision of these pulses is astonishing, with some pulsars ticking like cosmic clocks, their periods measurable to within microseconds. The fastest known pulsars, called millisecond pulsars, can spin hundreds of times per second. This rapid rotation is often due to the neutron star being spun up by accreting matter from a companion star in a binary system. Pulsar glitches are sudden changes in the rotation rate of a pulsar. These events are thought to be caused by a transfer of angular momentum between the superfluid interior of the neutron star and its solid crust. The crust, which is incredibly rigid, can suddenly crack or shift, causing a portion of the superfluid to be dragged along with it. This transfer of momentum causes the pulsar to spin up slightly, resulting in a glitch. Glitches can also be accompanied by a temporary increase in the pulsar's radio emission. The study of pulsar glitches provides valuable insights into the internal structure and dynamics of neutron stars. For example, the size and frequency of glitches can reveal information about the superfluid properties and the magnetic field strength within the star. Some pulsars glitch regularly, while others do so infrequently or not at all. The Crab pulsar, for instance, is known to glitch every few years. Understanding these events helps astronomers probe the extreme physics of neutron stars, offering a window into the behavior of matter under conditions that cannot be replicated on Earth. Pulsar wind nebulae. Neutron stars, the ultra-dense remnants of massive stars that have gone supernova, are among the most extreme objects in the universe. These celestial bodies pack the mass of the Sun into a sphere just a few kilometers across. Their formation occurs when a star, at least 8 times the mass of the Sun, exhausts its nuclear fuel. The outer layers of the star collapse onto the core, which then implodes under gravity's relentless pull. This cataclysmic event triggers a supernova explosion, leaving behind a neutron star. The core's collapse is so intense that protons and electrons are crushed together, forming neutrons. Hence, the name neutron star. Pulsars are a subset of neutron stars that emit beams of electromagnetic radiation. These beams are generated by the neutron star's magnetic field, which is incredibly strong, billions of times more powerful than Earth's. As the neutron star rotates, these beams sweep through space like a lighthouse's beam sweeping across the sea. If Earth happens to lie in the path of one of these beams, we detect it as a regular pulse of radiation. This is why these objects are called pulsars. The pulses are incredibly regular, making pulsars some of the most precise clocks in the universe. Some pulsars rotate hundreds of times per second, while others take several seconds to complete a single rotation. Pulsar wind nebulae form when the intense radiation and particles emitted by a pulsar interact with the surrounding interstellar medium. The pulsar's wind, composed of charged particles and electromagnetic radiation, creates a complex and dynamic environment. This wind can be so powerful that it carves out a cavity in the surrounding gas and dust, creating a nebula that glows in various wavelengths of light. The Crab Nebula, one of the most famous examples, is a pulsar wind nebula powered by the Crab pulsar. The nebula's intricate filaments and dynamic structure are shaped by the pulsar's wind, which interacts with the material ejected during the supernova explosion that created the neutron star. The study of pulsar wind nebulae provides valuable insights into the physics of neutron stars and the behavior of matter and radiation in extreme environments. These nebulae serve as laboratories for testing theories of particle acceleration and magnetic field dynamics. They also help astronomers understand the life cycles of massive stars and the processes that lead to the formation of neutron stars and pulsars. By observing pulsar wind nebulae, scientists can probe the nature of the universe's most exotic objects and unravel the mysteries of the cosmos. Binary pulsars. In the vast cosmos, neutron stars stand as some of the most enigmatic and fascinating objects. Born from the supernova explosions of massive stars, these stellar remnants are incredibly dense, with a teaspoon of neutron star material weighing billions of tons on Earth. Their formation begins when a massive star, typically more than 8 times the mass of our Sun, exhausts its nuclear fuel. The star's outer layers collapse onto the core, and the core itself collapses under gravity, crushing protons and electrons into neutrons. This process leaves behind a city-sized object with a mass of 1 to 2 suns, primarily composed of neutrons. The immense gravitational forces during this collapse also cause the star to spin rapidly, sometimes hundreds of times per second. Pulsars, a subset of neutron stars, are nature's most precise celestial clocks. They emit beams of electromagnetic radiation, primarily in the radio spectrum, from their magnetic poles. As these poles do not align with the star's rotational axis, the beams sweep through space like a lighthouse's light. When one of these beams sweeps past Earth, astronomers detect it as a regular pulse of radiation. This regularity is astonishing, with some pulsars having periods so consistent that they rival the accuracy of atomic clocks. The fastest known pulsars, called millisecond pulsars, spin at rates of up to 700 times per second. Their extreme rotational speeds and intense magnetic fields make them invaluable tools for studying the laws of physics under extreme conditions. Binary pulsars, as the name suggests, are pulsars that are part of a binary star system. These systems consist of a pulsar and a companion star, which can be another neutron star, a white dwarf, or even a main sequence star like our Sun. The study of binary pulsars has provided profound insights into the nature of gravity, space, and time. One of the most famous examples is the binary pulsar PSR B1913+16, discovered by Joseph Taylor and Russell Hulse in 1974. This system, consisting of two neutron stars, orbits each other in a tight, fast orbit. The gravitational waves emitted by this system cause the orbit to decay over time, a phenomenon that was predicted by Einstein's theory of general relativity. The precise timing of the pulsar's pulses allowed astronomers to measure this decay, providing strong evidence for the existence of gravitational waves. The study of binary pulsars also sheds light on the dynamics of stellar evolution and the behavior of matter in extreme gravitational fields. In some cases, the companion star can transfer mass to the pulsar, leading to complex interactions and phenomena. For instance, in a system called a low-mass 10th-ray binary, the companion star can lose material to the pulsar, forming an accretion disk around the neutron star. This material heats up and emits 10th rays, making these systems visible in the 10th ray spectrum. The study of these systems provides a unique laboratory for understanding the physics of accretion, magnetic fields, and the behavior of matter under extreme conditions. Additionally, binary pulsars can serve as natural laboratories for testing theories of gravity, as their orbits and interactions are influenced by the curvature of spacetime. Pulsar planets. In the vast expanse of the cosmos, neutron stars stand as some of the most enigmatic and fascinating objects. Born from the supernova explosions of massive stars, these stellar remnants are incredibly dense, with a teaspoon of neutron star material weighing billions of tons on Earth. Their formation is a dramatic process. When a massive star exhausts its nuclear fuel, it can no longer counteract the immense gravitational forces pulling it inward. The star's core collapses under its own gravity, leading to a supernova explosion. The outer layers of the star are blasted into space, while the core collapses into an ultra-dense neutron star. This process is so violent that it can briefly outshine entire galaxies. Pulsars, a subset of neutron stars, are known for their lighthouse-like behavior. They emit beams of electromagnetic radiation that sweep through space like a cosmic searchlight. This radiation is produced by the rapid rotation of the neutron star, which can spin hundreds of times per second. The beams are generated by the star's magnetic field, which accelerates charged particles to high energies. As the star rotates, these beams sweep through space, and if one of these beams points towards Earth, we detect it as a regular pulse of radiation. This is why these objects are called pulsars, short for pulsating stars. The discovery of planets orbiting pulsars has added another layer of intrigue to these already remarkable objects. The first exoplanets ever discovered were found around a pulsar, known as PSR B1257+12. These planets, dubbed pulsar planets, are quite different from the planets we find in our solar system. They are likely the remnants of a planetary system that survived the supernova explosion that created the pulsar. The extreme conditions around a pulsar make these planets some of the most inhospitable places imaginable. Intense radiation and gravitational forces make them unlikely candidates for life as we know it. Despite their harsh environment, the study of pulsar planets offers valuable insights into planetary formation and the resilience of planetary systems. These planets provide a unique laboratory for testing theories about planet survival in extreme conditions. Scientists can use the precise timing of pulsar signals to detect the tiny wobbles caused by orbiting planets. This method, known as pulsar timing, is incredibly sensitive and has allowed astronomers to discover and study these exotic worlds. The existence of pulsar planets challenges our understanding of planetary formation and survival, highlighting the diversity and resilience of planetary systems in the universe. Pulsars as cosmic clocks. Neutron stars are among the most fascinating objects in the universe. They form from the remnants of massive stars that have gone supernova. When a star much more massive than our Sun exhausts its nuclear fuel, it collapses under its own gravity. This collapse triggers a supernova explosion, leaving behind a dense core. If the core's mass is between about 1.4 and 3 times that of the Sun, it becomes a neutron star. These stars are incredibly dense, with a teaspoon of neutron star material weighing billions of tons on Earth. Their strong magnetic fields and rapid rotation make them unique laboratories for studying extreme physics. Pulsars are a special type of neutron star that emit beams of electromagnetic radiation. These beams are often observed as pulses of radiation, hence the name pulsar. The pulses occur because the beams are emitted from the magnetic poles of the neutron star, which are not aligned with its rotational axis. As the star spins, the beams sweep through space like a lighthouse beam sweeping over a landscape. If Earth happens to lie in the path of one of these beams, we detect it as a regular pulse of radiation. The precision of these pulses is astonishing, making pulsars some of the most accurate natural clocks known. The lighthouse analogy is particularly apt for understanding pulsars. Just as a lighthouse's rotating light appears to flash as it sweeps across the sky, a pulsar's rotating magnetic field produces beams of radiation that appear to pulse when observed from Earth. The rate at which these pulses occur is incredibly stable, often rivaling the precision of atomic clocks. This stability makes pulsars invaluable for various astronomical studies, including testing theories of gravity and detecting gravitational waves. Some pulsars spin hundreds of times per second, earning them the nickname millisecond pulsars. The mechanism behind pulsar radiation is complex and not fully understood. It involves the acceleration of charged particles along the star's magnetic field lines, which then emit radiation. This process is powered by the neutron star's rotation and magnetic field. Over time, pulsars slow down as they lose energy, but some can be recycled through interactions with companion stars, spinning them up to extremely high speeds. These recycled pulsars are often found in binary systems and are key objects of study for understanding the evolution of neutron stars and their environments. Their precise timing and high-energy emissions provide a wealth of information about the fundamental physics of these enigmatic objects. Pulsars and general relativity. Neutron stars, the ultra-dense remnants of massive stars that have gone supernova, are among the most extreme objects in the universe. These celestial bodies are so dense that a sugar cube-sized amount of neutron star material would weigh about 1 billion tons on Earth. When a massive star exhausts its nuclear fuel, it collapses under its own gravity, crushing its core to densities where protons and electrons are forced to combine into neutrons. The result is a neutron star, an object with the mass of the Sun compressed into a sphere just 10-20 kilometers in diameter. Some neutron stars exhibit intense magnetic fields and rapid rotation, emitting beams of electromagnetic radiation that sweep through space like cosmic lighthouses. These objects are known as pulsars. The radiation beams are not constant but pulse at extremely regular intervals, ranging from milliseconds to seconds, depending on the pulsar's rotation period. This pulsing effect is akin to a lighthouse beam sweeping across the landscape, hence the name. The mechanism behind this phenomenon is the rotation of the neutron star, which, combined with its magnetic field, accelerates charged particles and produces the observed radiation. General relativity, Einstein's theory of gravity, plays a crucial role in understanding the behavior of neutron stars and pulsars. The immense gravity of these objects warps space-time around them, causing effects that are predictable only through the lens of general relativity. For instance, the gravitational pull of a neutron star can be so strong that it bends the paths of light rays passing nearby, an effect known as gravitational lensing. Additionally, the rotation of neutron stars drags space-time around with them, a phenomenon called frame dragging. This effect has been observed in binary pulsar systems, where the pulsar's rotation influences the orbit of its companion star. Pulsars also serve as natural laboratories for testing general relativity. Their precise timing allows scientists to detect subtle effects predicted by the theory, such as the slowing down of time in strong gravitational fields, known as gravitational time dilation. One famous example is the binary pulsar PSR B1913+16, where the observed decay of its orbit matches the energy loss predicted by general relativity due to the emission of gravitational waves. These observations not only confirm the theory, but also provide insights into the nature of space-time itself. The study of pulsars and their interactions with general relativity continues to push the boundaries of our understanding of the universe. Pulsars and gravitational waves. Neutron stars are among the most fascinating objects in the universe. They form from the remnants of massive stars that have gone supernova. When a star much more massive than our Sun exhausts its nuclear fuel, it collapses under its own gravity. The core compresses so densely that protons and electrons combine to form neutrons, creating a neutron star. These stars are incredibly dense, with a teaspoon of neutron star material weighing billions of tons. They possess immense gravitational fields and magnetic fields that can be trillions of times stronger than Earth's. Pulsars are a special type of neutron star that emit beams of electromagnetic radiation. These beams are generated by the neutron star's magnetic field and rotate at incredibly stable rates, much like a lighthouse beacon. The radiation is emitted from the magnetic poles of the neutron star. As the star spins, these beams sweep through space. If one of these beams points towards Earth, we detect it as a pulsar. The regularity of these pulses is astonishing, with some pulsars ticking like cosmic clocks, their periods predictable to within microseconds over years. This precision makes them invaluable for various astronomical studies, including testing theories of gravity and detecting gravitational waves. Gravitational waves are ripples in the fabric of space-time, caused by massive, accelerating objects. Neutron stars, especially those in binary systems, are significant sources of these waves. As two neutron stars orbit each other, they lose energy by emitting gravitational radiation, causing their orbits to decay. This process accelerates as the stars get closer, leading to a dramatic increase in gravitational wave emission. In 2017, the LIGO and Virgo collaborations detected gravitational waves from a neutron star merger, an event also observed in electromagnetic radiation. This multi-messenger observation provided unprecedented insights into the physics of neutron stars and the origins of heavy elements like gold and platinum. The study of pulsars and gravitational waves has opened new windows into the universe. Pulsars act as natural laboratories for testing fundamental physics, including the behavior of matter at extreme densities and the nature of gravity. Gravitational waves, on the other hand, offer a unique way to probe the dark side of the cosmos, revealing phenomena that are invisible to traditional telescopes. Together, these cosmic lighthouses and space-time ripples are revolutionizing our understanding of the universe, offering glimpses into its most violent and enigmatic processes. The ongoing advancements in detector technology and observational techniques promise even more discoveries in the future, further unraveling the mysteries of neutron stars and the fabric of space-time. Pulsars and globular clusters. Globular clusters, dense collections of stars bound together by gravity, are stellar laboratories where the dynamics are intense and the interactions are frequent. Within these clusters, neutron stars, the ultra-dense remnants of massive stars that have exploded as supernovae, can form. These neutron stars are often found in binary systems, where their strong gravity can pull material from a companion star, leading to a variety of fascinating phenomena. One such phenomenon is the formation of millisecond pulsars, which are neutron stars that spin incredibly fast, completing hundreds of rotations in just 1 second. These pulsars are often found in globular clusters due to the high stellar density, which increases the likelihood of interactions and exchanges between stars. The mechanism behind pulsars is akin to a cosmic lighthouse. Neutron stars have intense magnetic fields, and as they spin, these fields channel jets of particles outward from the magnetic poles. If the magnetic axis is not aligned with the spin axis, these jets of radiation sweep through space like the beam of a lighthouse. When one of these beams sweeps past Earth, astronomers detect it as a pulse of radiation. This is why these objects are called pulsars. The regularity of these pulses can be extraordinarily precise, making some pulsars useful as natural clocks for astronomers. In the dense environment of globular clusters, the interactions between stars can cause neutron stars to spin up, transforming them into these rapidly rotating millisecond pulsars. In globular clusters, the high density of stars means that close encounters and interactions are common. These interactions can lead to the formation of binary systems involving neutron stars. In some cases, a neutron star can capture a passing star, pulling it into a close orbit. Over time, the neutron star can accrete material from its companion, spinning it up to high speeds. This process is thought to be the primary mechanism for the formation of millisecond pulsars in globular clusters. The presence of these pulsars provides valuable insights into the dynamics and evolution of globular clusters, as well as the properties of neutron stars themselves. The study of pulsars in globular clusters has revealed a wealth of information about these enigmatic objects. For instance, the globular cluster 47 Tucani is known to contain a large population of millisecond pulsars. Observations of these pulsars have shown that they can exhibit a range of behaviors, from stable, clock-like pulses to more erratic and complex patterns. Some pulsars in globular clusters have also been found to be part of exotic binary systems, including those with other neutron stars or even white dwarfs. These systems provide unique opportunities to test theories of gravity and stellar evolution. The dense environment of globular clusters, therefore, serves as a natural laboratory for studying the properties and behaviors of neutron stars and pulsars. Pulsars and gamma-ray bursts. Neutron stars, the ultra-dense remnants of massive stars that have gone supernova, are among the most extreme objects in the universe. These celestial bodies are so dense that a single teaspoon of neutron star material would weigh billions of tons on Earth. They form when the core of a massive star collapses under its own gravity during a supernova explosion. The protons and electrons in the star's core combine to form neutrons, hence the name neutron star. The intense gravitational collapse also causes the star to spin rapidly, sometimes hundreds of times per second. Pulsars are a special type of neutron star that emit beams of electromagnetic radiation. These beams are generated by the star's magnetic field, which is incredibly strong, billions of times stronger than Earth's. As the neutron star spins, these beams sweep through space like a lighthouse beam sweeping across the sea. If one of these beams happens to point towards Earth, we detect it as a pulsar. The regularity of these pulses is astonishing, making pulsars some of the most precise clocks in the universe. Some pulsars spin so fast that they complete hundreds of rotations in a single second, earning them the nickname millisecond pulsars. Gamma-ray bursts, GRBs, are the most violent and energetic events in the universe, releasing more energy in a few seconds than the Sun will in its entire lifetime. They are often associated with the collapse of massive stars or the merging of neutron stars. When a neutron star is part of a binary system, it can eventually merge with its companion, whether that companion is another neutron star or a black hole. This merger can produce a gamma-ray burst. The exact mechanism is still a topic of ongoing research, but it's clear that these events are incredibly powerful and can be detected across vast cosmic distances. The connection between pulsars and gamma-ray bursts is a fascinating area of study. Some pulsars are known to emit gamma rays, and these emissions can provide valuable insights into the physics of these extreme objects. For example, the Fermi Gamma Ray Space Telescope has detected gamma-ray pulses from many pulsars, helping scientists understand the processes that generate these high-energy emissions. The study of pulsars and gamma-ray bursts not only advances our understanding of neutron stars, but also sheds light on the fundamental forces and particles that govern the universe. Pulsars and the interstellar medium. Neutron stars, the remnants of massive stars that have exploded as supernovae, are among the densest objects in the universe. A typical neutron star packs more mass than the Sun into a sphere no larger than a city. The formation of a neutron star begins with the collapse of a massive star's core during a supernova explosion. As the core collapses, it reaches a point where the density is so high that protons and electrons combine to form neutrons, hence the name neutron star. The intense gravitational collapse is halted by neutron degeneracy pressure, preventing further collapse into a black hole. Some neutron stars exhibit a fascinating phenomenon. They emit beams of electromagnetic radiation that sweep through space like a lighthouse. These objects are known as pulsars. The beams are generated by the neutron star's magnetic field, which is incredibly strong, billions of times stronger than Earth's. As the neutron star rotates, the magnetic field lines sweep through space, accelerating charged particles and producing intense radiation. This radiation is emitted in narrow beams, and if one of these beams points towards Earth, we detect it as a pulsar. The regularity of these pulses is astonishing, making pulsars some of the most precise clocks in the universe. The interstellar medium, the matter and radiation that exist in the space between the stars, plays a crucial role in the behavior of pulsars. As pulsars emit their beams of radiation, they interact with the interstellar medium in various ways. One significant effect is the dispersion of the radio waves emitted by pulsars. The interstellar medium is not a perfect vacuum. It contains free electrons that cause the radio waves to slow down slightly. This dispersion depends on the frequency of the radio waves and the distance they travel through the interstellar medium. By studying this dispersion, astronomers can learn about the properties of the interstellar medium and the distance to the pulsar. Pulsars also contribute to the study of the interstellar medium through their interactions with it. The high-energy particles emitted by pulsars can create nebulae, glowing clouds of gas and dust. One famous example is the Crab Nebula, which is powered by the Crab pulsar. The pulsar's wind of particles interacts with the surrounding interstellar medium, creating complex structures and emitting radiation across the electromagnetic spectrum. These interactions provide valuable insights into the dynamics of the interstellar medium and the processes that govern the evolution of pulsars. Additionally, pulsars can be used as probes to study the interstellar medium's magnetic fields and turbulence, offering a window into the otherwise invisible aspects of our galaxy. Pulsars and the Milky Way. Neutron stars, the ultra-dense remnants of massive stars that have gone supernova, are among the most extreme objects in the universe. These celestial bodies are so dense that a sugar cube-sized amount of neutron star material would weigh about 1 billion tons on Earth. When a massive star exhausts its nuclear fuel, it collapses under its own gravity, triggering a supernova explosion. The core of the star, if it's between about 10 and 30 times the mass of the Sun, collapses into a neutron star. Electrons and protons in the star's core are crushed together to form neutrons, hence the name. This process releases an enormous amount of energy, causing the star to explode. The outer layers are blasted into space, leaving behind a rotating neutron star. Some neutron stars exhibit intense magnetic fields and rapid rotation, becoming what we call pulsars. Pulsars emit beams of electromagnetic radiation that sweep through space like a lighthouse's beam sweeping across the sea. These beams are created by the pulsar's magnetic field, which accelerates charged particles to near the speed of light. As the pulsar rotates, the beams sweep through space, and if one of these beams points toward Earth, we detect it as a pulse of radiation. The regularity of these pulses is astonishing, making pulsars some of the most accurate clocks in the universe. For instance, the pulsar PSR B1937+21, also known as the millisecond pulsar, spins at over 600 times per second, with a precision rivaling that of atomic clocks. In the Milky Way, pulsars are scattered throughout the galactic disk, often found in regions where star formation is active. Our galaxy is home to an estimated 100 million neutron stars, but only around 30 pulsars have been identified so far. The difference in numbers is due to the fact that pulsars are only detectable if their beams point toward Earth. Moreover, pulsars slow down and lose energy over time, eventually stopping their beams altogether. The study of pulsars in the Milky Way provides valuable insights into the life cycles of stars, the nature of matter under extreme conditions, and even the very fabric of spacetime. For example, the discovery of the first binary pulsar, PSR B1913+16, provided strong evidence for the existence of gravitational waves, a prediction of Einstein's theory of general relativity. Pulsars also play a crucial role in testing theories of gravity and the behavior of matter at nuclear densities. The Crab Nebula, a supernova remnant in the constellation Taurus, hosts a pulsar that spins about 30 times per second. This pulsar is a veritable cosmic laboratory, allowing astronomers to study the complex interplay between a rapidly rotating neutron star and its surrounding environment. The beams from the Crab pulsar are so powerful that they create visible wisp structures in the nebula, which can be observed changing over time. By studying these phenomena, scientists gain a deeper understanding of the fundamental forces and particles that govern the universe. Additionally, pulsars serve as natural probes for studying the interstellar medium, the thin gas and dust that permeate the space between stars. The dispersion of pulsar signals as they travel through this medium provides information about its composition and structure. Pulsars and the universe. Neutron stars are among the most exotic and fascinating objects in the universe. They form from the remnants of massive stars that have gone supernova. When a star several times more massive than our Sun exhausts its nuclear fuel, it can no longer counteract the immense gravitational forces pulling it inward. The star's core collapses under its own gravity, and the outer layers are blasted into space in a spectacular explosion. The core material is compressed to such an extreme density that protons and electrons combine to form neutrons, hence the name neutron star. A teaspoon of neutron star material would weigh billions of tons on Earth. These stars are incredibly dense, with a radius of about 10-20 kilometers, yet they can have a mass up to twice that of the Sun. Some neutron stars exhibit a remarkable phenomenon. They emit beams of electromagnetic radiation that sweep through space like a lighthouse. These objects are known as pulsars. The beams are generated by the neutron star's magnetic field, which is billions of times stronger than Earth's. As the neutron star rotates, the magnetic field lines whip around, accelerating charged particles and producing intense radiation. This radiation is emitted in narrow beams, typically along the magnetic poles. If one of these beams sweeps across Earth, we detect it as a regular pulse of radiation, hence the name pulsar. The pulses are incredibly precise, with some pulsars ticking like cosmic clocks, losing only a few milliseconds over millions of years. The lighthouse analogy is particularly apt for describing pulsars. Just as a lighthouse's rotating light sweeps across the landscape, a pulsar's beams of radiation sweep across the cosmos. The rotation rates of pulsars are astonishing. Some pulsars spin hundreds of times per second, while others rotate more slowly. The fastest known pulsar, PSRJ 1748-2446 AD, spins at an incredible 716 rotations per second. This rapid rotation can cause the neutron star to bulge at its equator due to centrifugal force, and over time, this can slow down the pulsar's rotation. The beams of radiation can be detected across the electromagnetic spectrum, from radio waves to gamma rays, providing astronomers with a wealth of information about these enigmatic objects. Pulsars play a crucial role in our understanding of the universe. They serve as natural laboratories for studying the behavior of matter and energy under extreme conditions. Pulsars also act as cosmic lighthouses, helping astronomers navigate the vast expanse of space. Their precise timing allows scientists to study gravitational waves, test theories of general relativity, and even search for signs of exotic matter. Moreover, pulsars can be used to detect planets outside our solar system. When a planet orbits a pulsar, it causes a slight wobble in the pulsar's rotation, which can be detected as a tiny variation in the pulse timing. This technique has led to the discovery of several extrasolar planets, including the first confirmed exoplanet, PSR B1257+12. As we wrap up our journey into the fascinating world of neutron stars and pulsars, let's take a moment to recap the cosmic spectacle we've explored. These incredible objects are born from the dramatic deaths of massive stars, where the core collapses under gravity's relentless pull, and protons and electrons merge to form a sea of neutrons. The result is a city-sized object so dense that a teaspoon of its material would weigh 1 billion tons. This is the neutron star, a cosmic marvel that defies our everyday understanding of matter. Now, imagine some of these neutron stars as cosmic lighthouses, spinning rapidly and emitting beams of radiation from their magnetic poles. As they spin, these beams sweep through space like a lighthouse's beam sweeping across the ocean. When one of these beams points towards Earth, we detect it as a regular pulse of radiation. This is the pulsar, a celestial beacon that helps us probe the mysteries of the universe. So, what's next in our exploration of the cosmos? Stay tuned for our upcoming video, where we'll dive into the enigmatic world of black holes. These gravitational giants have captivated scientists and stargazers alike, and we can't wait to share their incredible secrets with you. In the meantime, we'd love to hear from you. What's your favorite cosmic phenomenon? Is it the dramatic dance of neutron stars, the rhythmic pulse of pulsars, or perhaps something else entirely? Let us know in the comments below, and don't forget to like and subscribe for more mind-blowing journeys through the universe. Until next time, keep looking up and let the wonders of the cosmos inspire your imagination.